Good evening. Tonight, 100 things about the night sky that nobody has managed to explain yet. Here is the first. Almost everything out there is missing. Everything we can see, every star, every galaxy, every grain of dust, adds up to roughly 5% of what the universe is made of. Nobody knows what the rest is. Before we listen tonight to any single star, let us rest for a moment on something simpler and stranger, the plain darkness spread quietly between them, the wide black backdrop that makes the stars visible at all. It seems at first like the most obvious thing in the world. Of course, the night sky is dark, and yet astronomers have long known this to be genuinely puzzling, a gentle riddle called Olber's paradox, named for a German astronomer who wrote about it clearly in the early 1800s, though earlier thinkers had wondered over the same question long before him. If the universe were infinite in size, filled evenly with stars scattered through endless, unchanging space, then every direction your eye might wander should eventually meet the bright surface of some star, near or impossibly far, and the whole sky, by simple accumulation, ought to glow as brightly as daylight, with no true darkness ever falling at all. And yet it plainly does not, the sky above you now holding far more black than light. There is a quiet comfort in letting a puzzle this old, and this gentle simply rest with you for now, unsolved but unthreatening, before we drift softly onward. One of the calmest answers to this old puzzle concerns simple time, and how much of it the universe has actually had to work with. Space itself is not infinitely old, but began, as best we can measure, roughly 13.5 billion years ago, give or take, in the event cosmologists call the Big Bang. Because light travels quickly but not instantly, covering a fixed distance in a fixed stretch of time, there has not been enough time yet for light from the very farthest reaches of space to complete its long journey all the way to us, no matter how patiently we wait. This leaves us with what astronomers sometimes call the observable universe, a vast but genuinely limited sphere centered on our own small vantage point, beyond whose gentle edge lies still more space, and very likely more stars, whose light simply has not arrived yet, and will not for a very long time yet. So a good portion of the sky's darkness is not emptiness at all, but simply youth. Let this thought settle quietly into place now, calm and unhurried, before the night carries us gently on. A second gentle piece of this same answer involves motion, since the universe is not merely sitting still and aging quietly, but steadily expanding, carrying distant galaxies further from us with every passing year, stretching the space between us and them a little further with every moment. Light traveling toward us across these ever-growing distances gets stretched along with that space, its waves lengthened into what astronomers call redshift, so that light beginning its journey as ordinary visible light can arrive, after billions of years, shifted beyond what our eyes register, as quiet infrared rather than any color we could see. And setting that stretching aside, stars themselves are not eternal lamps burning without end, but finite objects, shining steadily for millions or billions of years and eventually fading. So the universe was never truly filled with endless, everlasting starlight to begin with. Between a universe still young, an expansion quietly stretching distant light away from visibility, and stars that simply do not shine forever, the darkness overhead begins to look considerably less mysterious. Rest easily with this small piece of arithmetic, unhurried, before we turn toward a rather different kind of darkness. Not all of the sky's darkness, though, comes from such vast cosmic distances, since some of it sits much closer to home, drifting within the edges of our own galaxy. Scattered through the spaces between stars lies a thin haze of gas and fine dust, material left behind by older stars and never gathered into anything new, and where a thick enough patch of it lies directly between us and a brighter field of stars beyond, that dust simply blocks the light from reaching us. Seen from Earth, such a patch appears not as a glowing cloud but as a dark silhouette, a starless gap against an otherwise crowded background, one well-known example being the coal sack, easily visible to the unaided eye near the Southern Cross, appearing to early observers almost like a hole cut cleanly out of the sky. These dusty clouds are called dark nebulae, and despite their shadowed appearance, many of them are actually busy, patient places, cool and dense enough within to let new stars slowly gather and form, entirely unseen behind their own dark curtain. Let this small truth rest quietly with you now, complete and unhurried, before we drift onward into the dark together. The dust behind these dark patches is extraordinarily fine, individual grains of carbon, and silicate smaller than the particles in ordinary household smoke, yet scattered across such distances that even this delicate material can hide whole fields of stars from view. This same dust also affects starlight that does pass through it, scattering blue wavelengths more readily than red, so stars seen through a thin veil of it appear redder and dimmer than they truly are, an effect astronomers must account for when measuring true stellar distances and brightness. For a long while, some of these patches were honestly mistaken for actual gaps in space, empty holes among the stars rather than clouds drifting in front of them. A puzzle resolved once photographic surveys in the early 20th century, comparing thousands of star fields, revealed the same dusty structures again and again, exactly where the darkness lay. It is a small, quiet fact that even the emptiest-looking corners of the night sky are very often not empty at all, only thoroughly hidden. There is no need to hold this precisely in mind, only to let it settle softly, the way everything tonight is gently allowed to rest. If we draw our attention away now from our own galaxy, out toward the very largest structures the universe has to offer, we find another, far grander kind of darkness waiting there. Galaxies themselves, it turns out, are not scattered randomly through space like sand across a beach, but gathered instead into a vast, softly glowing web of clusters and long filaments, strands of galaxies stretching across unimaginable distances, with enormous, comparatively empty regions filling the quiet spaces between them. These regions are called cosmic voids, and some of them are genuinely staggering in scale. One well-studied example, found in the constellation Boötes and sometimes nicknamed, rather fondly, the Great Nothing, stretching across several 100 million light-years, so enormous that light itself takes hundreds of millions of years simply to cross from one side to the other. Standing in our imagination, somewhere near the center of such a void, the surrounding sky would look strikingly, almost unsettlingly empty, holding only the faintest scattering of distant galaxies rather than the rich, familiar crowd we are used to picturing overhead. There is no rush anywhere in this, only the quiet, patient unfolding of one more vast and gentle fact. These voids are not simply accidents of scale, empty by pure chance, but genuine relics of the universe's own very early history, when matter was spread through space almost, though not quite perfectly, evenly. Even the tiniest variations in that early density, differences almost too small to properly imagine, gradually grew larger over billions of patient years, as gravity drew the slightly denser regions ever more strongly toward themselves, pulling in more surrounding material and leaving the already sparser regions beside them steadily emptier still. In this slow, unhurried way, the crowded filaments and clusters of today's universe and the vast, quiet voids resting between them both grew outward from the very same small beginnings, two sides of one long process stretched across nearly the whole age of the cosmos. A void, then, is not a flaw in the universe's design or a gap something failed to fill, but rather a genuinely meaningful part of its structure, exactly as significant in its own quiet way as any bright and crowded cluster of galaxies sitting nearby it. There is a steady comfort in knowing that even empty space keeps its own patient history, one settled thought resting easily beside the next. So far tonight, the darkness we have considered has mostly been a matter of light not yet reaching us, or light quietly blocked along its way, simple explanations once you sit with them a while. But there is another kind of darkness waiting in the universe, one considerably stranger and considerably less settled. In the late 1990s, two separate teams of astronomers, studying a kind of exploding star called a Type Ia supernova, whose peak brightness is reliably consistent enough to serve as a dependable cosmic measuring stick, noticed something nobody quite expected, that these distant explosions appeared fainter, and so farther away than a steadily expanding, gravity-slowed universe ought to allow. The simplest explanation turned out to be that the universe's expansion was not slowing down at all, as most astronomers had long assumed gravity should require, but speeding up instead, galaxies rushing apart a little faster with each passing year. Whatever is quietly responsible for this steady acceleration was given a plain, honest placeholder name, dark energy, a label that describes what it does far more confidently than it describes what it actually is. Let this rest now, honestly unresolved, before we sit together with it a little longer still. According to the most careful measurements available, this same dark energy makes up roughly 68% of everything the universe contains, easily its largest single ingredient, outweighing all of the stars, planets, gas, and glowing galaxies combined many times over. And yet, remarkably, nobody currently knows exactly what it is, only what it appears to do, acting like a steady, gentle pressure built into the fabric of space itself, growing stronger in total effect as space continues to expand. One leading idea treats it as a simple property of empty space, a constant, built-in energy that never dilutes no matter how much room it comes to fill, an idea often called the cosmological constant. Other, more exotic proposals imagine some slowly shifting field spread quietly through the universe instead, its true nature still entirely open for careful study and honest debate. Of everything considered tonight so far, this is perhaps the plainest, most honest mystery of them all, a vast majority of the universe's own content standing quietly beyond our present understanding. None of this needs solving tonight, only a calm, honest noticing, before we let it rest beside everything else we have quietly gathered. As this first chapter settles toward its close, it is worth holding its whole shape together a moment. All the ordinary matter we have ever touched or measured, every star, every planet, every breath drawn on any world, amounts to only about 5% of the universe's content, a strikingly small slice. Roughly another quarter is something else again, a separate puzzle called dark matter, studied more fully in a chapter ahead, while the larger remaining share belongs to the dark energy we have only just met, outweighing everything else combined. Even the faint glow lingering across the whole sky, after every known star, galaxy, and scrap of scattered light has been counted and subtracted, has not been fully explained down to its last trace, a small residual glow whose source remains unresolved. So the darkness above you tonight is no simple emptiness, but a patient, layered mystery, mostly unfinished business quietly waiting its turn. Later, we turn from watching this same dark sky toward listening to it instead, for whatever faint signals it may carry. Let this first chapter rest now, quiet and complete, held gently in your mind, before we drift on to whatever waits softly ahead. Long before any of this, the night sky had already been speaking to us in a language most people never notice. Not the language of starlight, but the quieter language of radio waves, faint ripples of energy pouring down constantly from stars and distant clouds of gas, invisible to the eye alone. Radio astronomy grew out of a chance discovery in the early 1930s, when an American engineer named Carl Jansky, working for Bell Telephone Laboratories and trying only to track down the source of faint background static troubling early radio communications, noticed a steady hiss that shifted its position slowly with the stars rather than with the sun, and traced it eventually towards the center of our own galaxy. From that modest, almost accidental beginning grew an entire branch of astronomy built around enormous dishes and patient listening, rather than lenses and glass. Tonight, we turn away from the visible sky for a while and lean instead towards this quieter, humming ocean of radio noise, and towards a small handful of signals within it that listeners have never fully managed to explain. There is a quiet, settled comfort in resting for a moment with this thought before we move gently onward. On the evening of the 15th of August, 1977, a large radio telescope known as Big Ear, run by Ohio State University near Delaware, Ohio, was quietly scanning the sky, recording faint signals onto a long computer printout rather than watching them live. Some days later, a volunteer astronomer named Jerry Amon sat down to review pages of numbers and letters representing signal strength, and found one sequence unlike anything he had seen before, 6 characters far stronger than the ordinary background hiss of the sky. Without quite thinking, he circled it in red pen and scrawled one word beside it, "Wow," giving the signal its lasting name. The signal lasted about 72 seconds, the time its fixed beam took to sweep past that patch of sky as the Earth turned beneath it, arriving on a frequency closely linked to neutral hydrogen, the universe's most common element. Despite many careful searches of that patch of sky in the decades since, it has never been detected again, and no one has ever fully agreed on what it was. Let this small detail rest easily in your mind now, unhurried and complete, before we continue softly on. Somewhere out across the universe, an entirely different kind of radio mystery flickers on and off almost constantly, a phenomenon astronomers call a fast radio burst, a pulse of radio energy lasting only a few thousandths of a second, yet carrying roughly as much energy as the sun releases over a span of days or longer. The first such burst was noticed in 2007, when astronomer Duncan Lorimer and a student reviewing archived data from the park's radio telescope in Australia found one bright spike that did not resemble anything catalogued before, a discovery that came to be known as the Lorimer burst. For years afterward, such bursts remained rare, puzzling curiosities, but newer instruments, especially a Canadian telescope called CHIME, built to scan the northern sky nightly, have since caught thousands of them, arriving from galaxies so distant that their light had been traveling towards us for a very long time indeed. Most appear to originate far beyond our own galaxy, flashing once and vanishing, their sheer distance making that brief burst of energy all the more remarkable to consider. It is a small, patient fact, offered gently, with nothing more required of you than simply to listen. Most fast radio bursts behave exactly as their name suggests, arriving once briefly and then never again from that same patch of sky, which led early researchers to imagine some sudden, violent, one-time event as the likely cause. In 2016, however, astronomers announced something that quietly reshaped this picture. A burst first spotted in 2012 was found to repeat, flashing again from the very same distant dwarf galaxy over months of careful watching, meaning whatever produced it had survived its own outburst and could do so more than once. Since then, a growing number of repeating sources have been identified alongside the far larger number that have still only ever been seen once, leaving researchers with a genuinely open question: whether these represent two different kinds of source or simply the same kind of object caught by chance at different stages of its life. Tonight, whichever kind of burst might be crossing the sky above us at this very moment, repeating or solitary, it arrives already having traveled for longer than the whole of human history. Nothing here needs to be held onto carefully, only received quietly, the way this whole night is meant to be received. For a long while, the true source of these fast radio bursts remained mostly a matter of careful speculation. Many theories proposed and set aside, until the spring of 2020 offered the first solid clue, when a dense, powerfully magnetic collapsed star called a magnetar, well within our own galaxy, let out a sudden burst of radio energy that telescopes on Earth, including the same chime instrument, caught in the act. This was the first time a fast radio burst had been traced, with real confidence, back to one specific known object, confirming that at least some of these bursts come from magnetars, dense stellar remnants wrapped in magnetic fields far stronger than anything producible on Earth. Even so, this single confirmed case has not settled the wider question, since most fast radio bursts detected so far come from galaxies so distant that pinning down their exact source, star by star, remains far beyond current instruments, leaving open whether every burst shares this same origin, or whether several different kinds of objects produce a broadly similar flash. Let it settle now, slowly and completely, before we turn our attention to whatever waits gently ahead. For years, staff at the park's radio telescope in Australia, the same dish once used to relay pictures from the Apollo moon landings, kept noticing strange, burst-like signals appearing only during daytime working hours, never at night, a pattern odd enough that researchers named them puritans, and puzzled over what cosmic source could behave on such a tidy schedule. The answer, reached in 2015 after good-humored detective work, turned out to have nothing to do with the distant universe at all. The puritans were traced instead to the observatory's own kitchen, to a microwave oven that sent out a burst of stray radio energy whenever a staff member opened its door too early, interrupting the cycle before it had finished. Once the oven's timing was adjusted, the mysterious daytime signals stopped entirely, a tidy, quietly amusing resolution to a puzzle that had troubled researchers for years. It stands now as a gentle reminder that even the most sensitive instruments built to listen to the far universe must still filter out the small, ordinary noises of the building around them. There is nothing urgent in any of this, only the slow, steady unfolding of one more small and gentle truth. Listening for signals that might come from another civilization, rather than from any natural star or cloud of gas, has its own history, beginning in 1960 when a young astronomer named Frank Drake pointed a radio telescope in West Virginia towards two nearby sun-like stars, Tau Ceti and Epsilon Eridani, in a modest effort he called Project Ozma, the first serious search of its kind. Since then, the search for such signals, known by the initial SETI, has grown into an effort using large dishes, and more recently, projects such as Breakthrough Listen, which scans many nearby stars and the wide plane of our own galaxy for narrow signals unlikely to occur naturally. often watching the quiet stretch of frequency between the signals given off by hydrogen and by hydroxyl. After more than 6 decades of patient listening, no confirmed signal has ever been found, and researchers today describe that long silence not as failure, but as a genuine scientific result in its own right, one that quietly shapes how we think about our own place within a largely silent universe. Rest with this a moment longer, unhurried, before the night carries us softly towards its next quiet detail. A radio telescope works on a principle simple enough to picture even in the dark. A large curved dish, shaped like a shallow bowl, gathers faint radio waves from across the sky and reflects them inward towards a single receiver above its surface, much as a mirror gathers light, though tuned to wavelengths far too long for any human eye to notice. Because a single dish is limited by its physical size, astronomers long ago developed a technique called interferometry, linking several smaller telescopes together, scattered across a continent or even a whole planet, combining their signals so the result behaves as though it came from one vast dish far larger than any single instrument could be built. Facilities such as the Very Large Array in New Mexico, its dishes arranged along wide desert tracks, rely on this combination of many smaller eyes acting together as one. Because faint cosmic whispers are easily drowned out by ordinary radio noise, from mobile telephones to the odd microwave oven, these instruments are generally built in remote, protected valleys, official quiet zones where nearby broadcasting is kept to a minimum. It asks nothing of you now except your calm attention, offered freely, before we drift onward together. For much of radio astronomy's early history, a night's listening did not appear on a glowing screen, but unrolled slowly across paper. Wide rolls of chart paper marked by an ink pen tracing the rise and fall of signal strength, or later, long stacks of computer printout covered in rows of numbers and letters representing that same strength hour by hour. Observers reviewing this paper record worked through an enormous quantity of it by hand, tracing each line with a pencil or a finger, watching for any small bump worth a second look, a method different from the instant digital alerts many instruments rely upon today. It was exactly this kind of printout that a young astronomer once sat reviewing, page after page, before finding one unusual sequence worth circling in red, and exactly this kind of chart that other young researchers combed through by hand, sheet by sheet, in searches leading somewhere else entirely. Tonight, it is worth picturing those quiet rooms full of rolled paper and steady ink lines, records slowly accumulating while the sky above went on doing exactly what it always does. Such small, steady facts are exactly what this long night is made of, one gentle thought following another. The telescope that caught the wow signal did not survive long enough to see its own mystery settled. Big Ear was never really a dish in the ordinary sense at all, but a flat field of aluminium and wire covering an area close to that of 3 football pitches. Built cheaply in the early 1960s and run for decades largely by volunteers. Its whole design resting on letting the Earth's own rotation carry the sky slowly past a fixed beam rather than moving anything heavy at all. It carried out the longest-running search of its kind anywhere, more than 20 years of patient listening on a budget that would embarrass most modern instruments, and in 1998 it was dismantled, the land beneath it sold and cleared to make room for an expansion of the golf course next door. Its most famous observation lasted 72 seconds and has never once been repeated. As this chapter of static, paper, and patient listening draws softly to its close, let it settle now, the printout circled in red, the oven caught out in the observatory kitchen, and one quiet field of wire that listened to the whole sky for 20 years and then was gone. Carry this soft hum of half-understood signals forward with you now, as the night drifts gently onward. Having spent some time now drifting quietly among the visible lights of the night sky, we turn our attention next towards something that cannot be seen at all, and yet without it, none of those lights would hold together in the patterns we recognize. Astronomers call it dark matter, a deliberately plain name for a substance that neither emits light, nor absorbs it, nor reflects it in any way our instruments can catch, detectable only through the quiet, patient pull of its gravity on everything nearby. Careful measurements across galaxies and clusters alike suggest that ordinary matter, the atoms making up stars and planets and every one of us, accounts for only a small share of the matter truly present, with something like 5 times as much again existing in this unseen form, threaded invisibly through every galaxy we know. This is not a fringe idea or a hurried guess, but a conclusion drawn slowly and carefully from many independent lines of evidence, gathered across nearly a century of careful looking, which we will walk through gently, one steady thread at a time. Let this quiet, open question settle over you now, unhurried, before we follow it further into the dark. In the 1970s, the American astronomer Vera Rubin, working closely with her colleague Kent Ford, turned her careful attention to the way stars move within spiral galaxies such as Andromeda, measuring their speeds at different distances from each galaxy's bright center, using the gentle shifting of light called the Doppler effect. By simple Newtonian expectation, stars orbiting far out at a galaxy's faint outer edge should move noticeably slower than those closer to the crowded, massive center, in much the same way that outer planets in our own solar system trail more slowly than Mercury or Venus. Instead, Rubin and Ford found that these outer stars kept moving just as quickly as those nearer the center, producing what astronomers now call a flat rotation curve, a pattern that made sense only if a great deal of additional, unseen mass were spread generously through and beyond the visible disk of each galaxy. She studied dozens of spiral galaxies over the following years, finding this same flat, steady pattern again and again, quiet and consistent evidence that reshaped how astronomers understood galaxies entirely. Let this steady, patient measurement rest now in your mind, one careful astronomer's long attention settling gently into certainty. Decades earlier, in 1933, the Swiss astronomer Fritz Zwicky had already noticed something quietly strange while studying the Coma cluster, a great gathering of thousands of galaxies bound together by gravity and lying a few 100 million light years from where we now rest. Measuring how quickly individual galaxies within this cluster moved relative to one another, using the same careful spectroscopic methods that would later guide Vera Rubin's own work, Zwicky applied a well-established piece of physics called the virial theorem, which relates the speeds of orbiting bodies to the total mass holding them together. The galaxies were moving far too quickly for the visible starlight of the cluster to be holding them in place at all, so quickly that the whole cluster should, by ordinary expectation, have flown apart long before Zwicky ever pointed his instruments toward it. To explain this quiet discrepancy, he proposed that some additional, unseen mass must be present, giving it the German name Dunkelmaterei, dark matter, a term that would wait patiently for decades before the wider astronomical community returned to it with the attention it deserved. Rest with this early, overlooked insight a while longer, before we follow its slow, patient path forward. General relativity, the theory of gravity published by Einstein in the early 20th century, describes mass not as pulling on light directly, but as gently curving the very space light travels through, bending its path in a way that ordinary Newtonian gravity never quite predicted. When a massive foreground cluster of galaxies happens to sit between us and some much more distant background galaxy, its combined gravity, nearly all of it invisible, bends the background light around it, an effect astronomers call gravitational lensing, borrowing its name from the familiar way a glass lens bends light toward a focus. The more mass a cluster contains, visible and invisible together, the more strongly it bends this passing light, which means the pattern and strength of the resulting distortion can be measured and used, quite literally, to weigh a cluster's total mass without ever needing to see most of it directly. This technique has become one of astronomy's most trusted tools for mapping unseen matter, turning the gentle curve of distant starlight into a careful, patient scale for something that would otherwise remain entirely hidden from view. Let this quiet trick of bent light settle now, gently, before we look more closely at its patterns. When the alignment between a distant background galaxy, a massive foreground cluster, and our own patient telescopes happens to fall almost perfectly into a single straight line, the bent light traveling around the foreground mass can form a striking closed loop known as an Einstein ring. The background galaxy's light smeared symmetrically into a thin, glowing circle surrounding the cluster at its center. Less perfect alignments, considerably more common, tend to produce long, gently curved arcs instead, elegant streaks of stretched light draped across images of massive clusters, each one a background galaxy's ordinary shape pulled patiently out of true by gravity it cannot resist. Astronomers examining these arcs and rings can work backward with real precision, calculating exactly how much total mass would be needed to produce such a particular pattern of bending, consistently finding far more mass than any visible galaxy or hot gas cloud could possibly account for alone. These graceful, curved distortions, first captured clearly in cluster images during the 1980s, remain some of the most quietly beautiful direct evidence for unseen mass that astronomy possesses. Let these soft arcs of borrowed light rest in your mind a while before we turn gently onward. The unseen mass surrounding a typical galaxy does not sit flat within its bright spiral disk the way stars and gas so visibly do, but instead spreads outward in a roughly spherical shape astronomers call a dark matter halo, extending well beyond the galaxy's visible edge like some vast, invisible cloud cradling something much smaller and brighter at its center. This halo is thought to contain the great majority of a galaxy's total mass. With the shining disk of stars, we actually photograph representing only a modest inner portion, embedded deep within a far larger structure we cannot see directly at all. Such a halo explains rather neatly why stars at a spiral galaxy's outer edge keep orbiting as quickly as Vera Rubin and Kent Ford once found, since they remain held firmly within this extended, unseen mass long after the visible starlight around them has begun to thin and fade. Even our own Milky Way is thought to sit at the center of just such a halo, one reaching several times further into space than its familiar spiral of stars ever does. Carry this quiet image gently forward now, a bright galaxy cradled inside something vast and unseen, before we rest a while longer. Among all the evidence gathered for unseen mass, few examples speak as plainly as the Bullet Cluster, the informal name given to a pair of galaxy clusters caught in the act of colliding, roughly 3.5 billion light-years from where we now rest. Observations made in 2006 combined two different kinds of evidence: X-ray images revealing hot, glowing gas that had collided, slowed, and dragged behind during the encounter, and separate gravitational lensing maps revealing where the cluster's true mass actually sat, calculated from the bending of light passing through them. These two maps, gas and mass, did not line up at all. The hot gas sitting slowed near the collision center, while the bulk of each cluster's gravity, unseen and seemingly untouched by the impact, had passed cleanly through and continued onward ahead of it. Since ordinary matter and dark matter were expected to behave quite differently in exactly this kind of violent encounter, unseen mass passing through with little resistance while gas collides and slows, this clean separation offered astronomers a rare, almost visual confirmation that something more than ordinary matter truly was present. Let this quiet cosmic collision settle now in your thoughts before we drift onward together. Zoom out far enough, well beyond any single galaxy or cluster, and the universe's galaxies do not scatter about randomly, but instead trace out a vast, faint structure astronomers have come to call the cosmic web. Long threads and filaments of galaxies stretching across hundreds of millions of light years, meeting occasionally at denser knots where great clusters gather. Computer simulations built from our understanding of gravity and unseen mass reproduce this same delicate, thread-like pattern with remarkable faithfulness, suggesting that dark matter forms the underlying scaffolding of the whole structure, its gravity gathering ordinary gas and galaxies gently along invisible filaments the way morning dew gathers quietly along the fine threads of a spider's web. Visible galaxies, bright and countable, mark only the places where this unseen scaffolding happens to be dense enough to gather ordinary matter into shining points, while the filaments themselves remain otherwise dark, their presence inferred rather than directly photographed. Large surveys mapping the positions of hundreds of thousands of galaxies have traced this web across enormous stretches of sky, confirming, patiently and repeatedly, a structure first suggested by careful calculation alone. Rest with this vast, quiet architecture a moment longer, before the night carries us gently onward. In 1995, the Hubble Space Telescope was pointed for many patient days toward a small, seemingly empty patch of sky near the constellation Ursa Major, gathering faint light steadily to produce the Hubble Deep Field, an image that revealed not emptiness at all but several thousand previously unseen galaxies crowded into a sliver of sky no wider than a grain of sand held at arm's length. Later efforts pushed further still. The Hubble Ultra Deep Field in 2004, and more recently, the James Webb Space Telescope's own deep field images, reaching galaxies fainter and more distant than any observed before, their light having traveled toward us for billions of patient years. Some of these deep images happen to include massive foreground galaxy clusters, and within them, astronomers find exactly the gentle arcs that gravitational lensing predicts. Faint background galaxies stretched by unseen mass into soft, curved streaks scattered quietly among the sharper shapes nearer at hand. Each such image stands as a patient, layered census of the universe, ordinary galaxies and invisible mass alike, recorded together in a single long, careful exposure. Let this crowded, quiet sky settle now in your mind before we turn to a rather different kind of search. Deep beneath the ground, in old mines shielded from the ordinary static of cosmic rays, physicists have spent several decades running patient experiments designed to catch a single direct collision between a dark matter particle and an ordinary atomic nucleus, using tanks of ultra-pure liquid xenon and other shielded detectors watching quietly for the faintest flicker. Despite this long effort, stretching back to the 1980s and continuing today, no experiment has yet produced a confirmed, repeatable detection of such a particle, leaving its true identity one of astronomy's most honestly open questions rather than a settled fact. A smaller number of researchers have pursued a different explanation, modified Newtonian dynamics, or MEND, proposed by the physicist Mordechai Milgram in 1983, suggesting gravity itself behaves differently at the faint accelerations found at a galaxy's outer edge, removing the need for unseen mass entirely. Mind explains many individual galaxy rotation curves elegantly, yet struggles with larger structures such as colliding clusters, part of why most astronomers still favor unseen mass as the simpler explanation. Let this whole quiet chapter of invisible mass, rotation curves, bent light, and patient underground listening rest gently now, before the night carries us onward to whatever question waits quietly next. Not every planet drifting through the darkness belongs to a star, and among the quietest mysteries the night sky keeps are the rogue planets, sometimes called free-floating planets, worlds that travel alone through the space between stars, warmed by no sunrise and dimmed by no sunset, since no sun is near enough to offer either. Some of these solitary worlds were likely born the ordinary way, forming within the swirling disk of gas and dust around a young star, only to be flung outward later by a passing planet's gravity or a close encounter with another star, cast loose into the emptiness between one system and the next. Others, according to some researchers, may never have belonged to any star at all, condensing directly from a collapsing clump of gas within a nebula, as a small star might, yet never gathering enough mass to ignite. Somewhere above you tonight, in the quiet distances between the stars, uncounted worlds like this may be passing slowly through the dark, each carrying its own frozen, sunless night that never breaks into morning. There is no rush in any of this, only the same slow, settling pace this whole quiet night has kept from its very start. Finding a planet that gives off no light of its own and orbits no star to reflect any presents astronomers with a peculiar challenge, solved mainly through a technique called gravitational microlensing, which depends not on seeing the planet directly, but on watching what its gravity does to a star's light passing far behind it. When such a planet drifts between Earth and a distant background star, its gravity bends and focuses that star's light like a natural lens, brightening it for hours or days before fading back to normal. A brief shimmer that, once measured, betrays the mass and distance of the invisible wanderer that caused it. Large surveys scanning millions of stars toward our galaxy's crowded center, watching night after night for this kind of flicker, have caught dozens of such events over the years, each a fingerprint left by something that would otherwise pass entirely unnoticed. A second method works only for the youngest rogue planets, still glowing faintly in infrared from leftover formation heat, before that warmth fades into the same cold dark surrounding them. Let this quiet method rest a moment in your mind before we follow it further into the dark it was built to reveal. Estimating how many of these starless worlds actually exist means reasoning carefully from a small number of chance detections outward to the whole galaxy. And the resulting numbers, while genuinely uncertain, are strikingly large by any ordinary measure. One influential study of microlensing data, published in the early 2010s, suggested that Jupiter-sized rogue planets alone might outnumber the ordinary stars of the Milky Way by roughly 2 to 1, implying a population easily running into the hundreds of billions once every galaxy of similar size across the universe is considered. Smaller, rockier rogue worlds are thought to be harder still to detect through microlensing, since their gravity produces a fainter and much briefer signal, meaning the true total, if smaller planets are counted too, could climb a good deal higher than even these already considerable figures suggest. Scientists remain careful to note how much uncertainty still surrounds these totals, since so few confirmed events exist to reason from. Yet even the most cautious estimates leave the galaxy populated by a genuinely vast, largely invisible population of solitary drifting worlds. Such uncertain, patient numbers are enough for now, offered gently, with nothing more required of you than to let them settle quietly. The surface of a rogue planet, cut off from any star's warmth, would lie in permanent, near-total darkness, its sky lit merely by the faint glow of other stars scattered across the galaxy. No brighter than our own night sky appears from a rooftop far from any city. Without a sun to warm it, such a world's surface temperature would sink to within a handful of degrees of absolute zero, cold enough that any atmosphere it once carried would freeze solid, settling as a thin frost across the ground, snow made not of water but of air itself. Yet this cold may not be the whole story everywhere, since a large enough rocky world could generate faint warmth deep within, heat left from its formation or produced by slow radioactive decay in its core, possibly enough, some researchers propose, to keep a hidden ocean liquid beneath a thick shell of ice. Such a world offers no dawn, no dusk, and no season worth naming, only the same patient dark stretching in every direction, for as long as its solitary journey continues. There is a strange, quiet comfort in cold this complete, resting here a moment before we drift further onward. In 2023, the James Webb Space Telescope turned its infrared eye toward the Orion Nebula, a vast stellar nursery roughly 1,350 light-years away, where thousands of young stars are still forming, and returned an observation that genuinely puzzled the astronomers studying it. Scattered through the nebula, it identified around 40 pairs of free-floating objects, roughly 80 bodies in total, each with a mass somewhere near Jupiter's, some barely heavier and others several times more massive, yet none orbiting any star at all, each instead paired loosely with a companion of similar size. Researchers gave these strange pairings the informal name JUMBOs, short for Jupiter Mass Binary Objects, a label capturing how peculiar they are, too small and light to be considered even the dimmest star, yet found in matched pairs drifting freely through space in a way standard theories of star and planet formation struggle to explain. Nothing quite like this had been documented in such numbers before, adding a genuinely fresh puzzle to the growing list of things the night sky still holds just out of science's understanding. Let this small mystery settle now, gently, exactly as it is, unresolved and entirely undisturbed. Two competing explanations have been offered for how the JUMBOs might have come to exist, and neither one fits especially comfortably. The first suggests they were ejected as already paired objects from young, crowded star-forming systems, flung outward together by close encounters with other forming stars or planets. Yet simulations of such violent ejections generally predict that a loosely bound pair like this ought to be torn apart, rather than escaping neatly together and intact. The second proposes that these pairs formed directly where they now sit, condensing from small, collapsing clumps of gas and dust within the nebula, in miniature imitation of how ordinary binary stars are born, except that the clumps involved would need to have been unusually small, never gathering nearly enough mass to ignite as even the faintest star. Many of the observed pairs are separated by distances hundreds of times greater than the gap between Earth and the Sun, held together by only the gentlest gravitational grip, fragile enough that either explanation still leaves unresolved questions about how such delicate partnerships ever survived their own violent birth. Nothing here needs solving tonight, only noticing quietly, before the night carries itself softly onward. Far beyond Neptune, where sunlight has grown almost too faint to matter, a small population of icy bodies orbits the sun on paths that share something unusual. Several of the most distant, including a small world called Sedna, trace orbits that cluster together in orientation far more tightly than random chance would reasonably allow. Astronomers first noticed this quiet pattern in the early 2010s, and by 2016 two researchers had proposed a tidy explanation that the gravity of a large, still undiscovered planet, tentatively named Planet 9, might be shepherding these distant bodies into their strangely matching alignment from somewhere out in the dark beyond them. Such a planet, if it exists, is thought to carry several times the mass of Earth, following an orbit so wide and slow that a single circuit of the Sun could take 10 to 20,000 years to complete, a patience far beyond anything else known to orbit our star. Whether this quiet gravitational fingerprint belongs to a real, undiscovered world or to some other explanation remains one of the more tantalizing open questions hanging over the outer solar system tonight. Rest with this quiet pattern a moment longer before we turn gently toward what it might yet mean. Actually finding Planet 9, assuming it is truly there, has proven far harder than proposing it, for reasons that make good sense once you consider how distant and dim such a world would be. At a distance perhaps 20 times farther from the Sun than Neptune, any light reflected from its surface would arrive at Earth's telescopes almost impossibly faint, lost among the ordinary scatter of background stars, unless a survey is both deep enough to catch it and fortunate enough to be looking at exactly the right patch of an extremely large sky. Its slow, wide orbit compounds the difficulty, since a world moving this gradually against the background stars can be mistaken, in a single night's observation, for a star that simply is not moving at all, revealing itself only through careful comparison of images taken weeks or months apart. Newer, wider surveys, including deep sky mapping projects only recently coming online, are expected to cover far more of the sky at the depth needed than earlier searches managed, offering a reasonable chance of confirming or quietly ruling out this distant possibility within the coming years. It is enough for now simply to let this unseen, hypothetical world rest undiscovered a little longer. The neighborhood where Planet 9 is thought to hide forms only the nearer part of a larger region encircling our solar system, beginning with the Kuiper Belt, a broad ring of icy bodies starting beyond Neptune's orbit and stretching outward for billions of kilometers, home to Pluto, several other dwarf planets, and countless smaller frozen fragments left from the solar system's earliest, most chaotic days. Farther out, at a distance that models place somewhere between a few thousand and perhaps 100,000 times the Earth-Sun gap, lies the Oort cloud, a vast, roughly spherical shell of icy debris proposed by astronomer Jan Oort in 1950. Never directly observed, but inferred confidently from the long, looping paths of comets that occasionally fall inward from every direction. Together, these two quiet reservoirs mark the true, gradual edge of our solar system, where the Sun's gentle grip grows too weak to hold on, giving way to the pull of neighboring stars and the wider turning of the galaxy itself. Somewhere past even this furthest icy shell, our own small solar system quietly ends, and the open dark between the stars properly begins. Let this vast, patient boundary settle now, unhurried, in your tired and slowly drifting mind. Occasionally, something drifts into our solar system from outside it, a visitor from another star passing through on a path that will never return. And in October of 2017, astronomers using the Pan-STARRS telescope in Hawaii confirmed the first such object recorded, a body named Oumuamua, a Hawaiian word for a scout reaching us from afar. What made it strange was its shape, unusually long and narrow, or perhaps flattened like a worn coin, tumbling rather than spinning smoothly, and its motion showing a small but measurable extra push as it departed, more acceleration than gravity alone could explain, without any visible tail or dust of the kind a comet sheds. Researchers have proposed careful, unglamorous explanations, perhaps a venting of hydrogen trapped within porous ice, or a fragment of frozen nitrogen broken from some distant, Pluto-like world, an unfamiliar icy body behaving in ways our own comets do not. A second interstellar visitor, Borisov, arrived 2 years later and behaved far more familiarly, glowing with a tail and ordinary dusty activity, a reminder that such lonely travelers between the stars are, most often, ordinary wanderers themselves. Carry this whole cold, drifting quiet forward with you now, gently, as the long night continues on. Nearly everything you see when you lift your eyes to the night sky is, quite simply, old news. Light that left its source long ago and has been traveling quietly through the dark ever since, until it reaches whatever eye happens to be waiting for it. Moonlight takes a little over a second to cross the gap between the moon and the earth. Sunlight takes a little over 8 minutes, and starlight, depending on the star, can be centuries old, thousands of years old, or sometimes considerably older than the earth itself. Astronomers who study this arriving light carefully, measuring its color, its brightness, its faint fluctuations, have learned an enormous amount about the universe's long and layered past. Tonight, somewhere above you, that same old light is quietly completing journeys begun long before this particular evening, long before almost anything familiar. And every so often, when this ancient light is measured carefully from 2 directions, the 2 answers refuse to agree, a small, steady thread we are going to follow gently now. There is no need to hold on to any of this too tightly, only to let it drift, unhurried, through your mind as we begin. In the middle years of the 1960s, 2 radio astronomers named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in Holmdel, New Jersey, testing a large horn-shaped antenna built originally for satellite communication, when they began picking up a faint, steady hiss arriving from every direction at once, regardless of season. Assuming the trouble lay with their own equipment, they checked the antenna thoroughly, and famously found a pair of pigeons nesting inside it, along with a layer of what they later described, delicately, as a white dielectric material, cleaned away carefully before testing the antenna once more. The strange hiss remained exactly as before, unaffected by pigeons, weather, or direction, and only after contacting physicists at nearby Princeton did the 2 men learn they had likely stumbled, quite by accident, onto the ancient afterglow of the universe's own hot beginning, cooled now to just a few degrees above absolute zero. Tonight, that same faint signal is still arriving, everywhere at once, filling the whole sky evenly, whether or not anything happens to be listening for it. Let that small, patient discovery settle now, quietly, before we follow the light a little further. Long before Penzias and Wilson found their patient hiss, astronomers had already noticed something peculiar about light arriving from distant galaxies, leaning consistently towards the red end of the spectrum. Its familiar spectral lines shifted from where laboratory measurements said they ought to sit. An American astronomer named Vesto Slipher, working at Lowell Observatory in the 1910s, was among the first to measure this shift across faint, distant spiral nebulae, and roughly a decade later Edwin Hubble, working with Milton Humason, connected this same reddening to distance, showing that the farther away a galaxy sat, the more strongly its light had reddened. The underlying cause, astronomers came to understand, was not motion through space in the ordinary sense, but the quiet stretching of space as light traveled across it, lengthening each wave gently, the way a slow breath might lengthen a single note. Tonight, above you, a great deal of the faint light reaching any nearby telescope has already reddened in exactly this way, some of it stretched only slightly, some stretched almost beyond easy recognition. There is nothing to work out here, only this one soft shade of red resting gently in your thoughts. Once astronomers understood that a distant galaxy's redshift could reveal how quickly the space between it and us is stretching, a natural next step was to measure that stretching precisely enough to give the whole universe a single, dependable expansion rate, a figure known as the Hubble constant. Two careful and largely independent methods have been used to reach this figure, one working backward from the ancient, evenly spread light of the cosmic background itself, analyzed in fine detail by the European Planck satellite, and another working forward from nearer stars and exploding stars called Cepheid variables and supernova, measured patiently by teams such as the one led by the astronomer Adam Rees. The trouble, quietly persistent now for a good many years, is that these two careful methods do not agree. The background light method settling near 67 kilometers per second per megaparsec, the nearer star method settling closer to 73, a gap that further precision has narrowed only slightly rather than resolved outright. Tonight, both of these patient, careful measurements continue quietly holding their ground, neither one willing yet to give way to the other. Let the two numbers rest quietly side by side for now, unresolved and entirely undemanding of you. Since beginning its careful survey of the sky in the summer of 2022, the James Webb Space Telescope has spent a considerable amount of its time gathering extremely faint, extremely old light from galaxies as they appeared within the universe's first few 100 million years. A period astronomers had long expected to look sparse, small, and only loosely organized. Instead, a number of these very early galaxies have turned up looking surprisingly large, surprisingly bright, and surprisingly well-formed, already containing more mature stars and more organized structure than most earlier models of galaxy growth had comfortably allowed for at such a young age. Researchers have spent the time since carefully checking these findings, considering whether brightness from actively feeding black holes at a galaxy's center might account for some of the apparent bulk, while other cases still appear to hold up as genuinely early and genuinely substantial. Tonight, that same faint and remarkably old light continues arriving patiently at Webb's wide, cold mirror, carrying pictures of a universe barely begun and already busier than expected. Let this simply sit with you a while, unhurried, one more early galaxy settling quietly into the dark behind us. In the first few minutes after the Big Bang, the whole universe briefly acted as a single enormous furnace, cool and spread out enough for protons and neutrons to combine into the very first atomic nuclei, a brief and well-understood process astronomers call primordial nucleosynthesis. The predictions this process makes for hydrogen and for ordinary helium match what astronomers actually observe in the oldest, most unspoiled gas and stars remarkably well. A quiet triumph of careful theoretical work meeting careful observation. Lithium, the third and lightest element made in any real quantity during this same brief period, tells a noticeably different story, since the amount predicted by the theory runs roughly 3 times higher than the amount actually measured across a broad, steady plateau of old, faint stars, first studied carefully by the French astronomers Monique and François Spite in the early 1980s. Tonight, that same small discrepancy, patiently measured and patiently remeasured for decades now, remains quietly unresolved, tucked away in the light of stars far older than almost anything else nearby. There is a plain, easy comfort in a puzzle this old, and this quietly unbothered by staying unsolved a little longer. Because starlight arrives so faintly after such a long journey, one of the oldest tricks available to any astronomer, professional or otherwise, is patience itself, leaving a shutter or a detector open for minutes or hours, or in certain cases many days, allowing faint old photons to accumulate quietly until a picture slowly emerges from what first looked like empty darkness. Point an ordinary camera at the sky for long enough without tracking the stars, and the Earth's own steady rotation will draw each star into a graceful curved trail across the image, circling slowly around a fixed point near the pole, a quiet reminder that it is the ground beneath us doing the turning. In 1995, astronomers pointed the Hubble Space Telescope at a small, seemingly empty patch of sky for roughly 10 days running, at the discretion of the observatory's director, Robert Williams, and the resulting image revealed several thousand faint galaxies previously hidden entirely from view. Tonight somewhere, a shutter very likely sits open in exactly this same patient way, gathering old light slowly, one quiet photon at a time. Let the shutter close now, gently on this thought, before the night carries us onward. For roughly a century, from the 1880s through to the 1990s, astronomers recorded the night sky not with digital sensors, but with large glass photographic plates, coated in a light-sensitive emulsion, and exposed patiently for hours at a time to catch as much faint starlight as each plate could hold. The Harvard College Observatory alone assembled a collection of more than 500,000 such plates across this same long century, an enormous archive studied for decades by a dedicated team of women astronomers, including Henrietta Swan Leavitt, Annie Jump Cannon, and Williamina Fleming, working carefully through plate after plate by eye and by hand. Held safely in cool, quiet storage long after their original exposure, these old plates still preserve real, measurable starlight from evenings that ended decades ago, and a modern scanning project has spent recent years working through them carefully, turning that whole archive into a century-long record of the changing sky. Tonight, somewhere in a climate-controlled room, stacks of this old glass rest quietly in the dark, each one still holding its own small, faithful slice of a much older night. Rest here a moment longer with this small glass and silver detail before we turn towards what follows. Gathering enough of this old, faint light to study properly comes down to a fairly simple piece of physics. A larger mirror collects more light, and for a long time that meant building a single mirror as large as anyone dared, such as the 200-inch mirror at the Hale Telescope on Palomar Mountain, ground and polished so carefully that the project took the better part of 2 decades to complete. Beyond a certain size, a solid mirror becomes impossibly heavy to support, which is why the twin Keck telescopes in Hawaii each carry 36 smaller hexagonal segments working together as one 10-meter surface, aligned to behave optically as one continuous mirror. The James Webb Space Telescope carries this same idea further, its 18 gold-coated hexagonal segments, each made of lightweight beryllium, unfolding carefully in space before settling into one wide, cold, 6.5-meter surface built to catch the faintest and oldest light available. Tonight, whichever mirror happens to be open to the sky, segmented or solid, is doing exactly this same quiet, patient work of gathering old light carefully together. Let this careful geometry of glass and gold rest quietly in your mind now, before we gather the whole chapter gently to a close. Put all of this together, and one plain fact sits quietly underneath it, that the oldest light reaching any telescope tonight has been traveling longer than the Earth itself has existed, since our own planet is a comparatively young 4.5 billion years old, while the most distant light Webb now catches has been traveling for more than 13 billion years. That means this light left its source before the sun had gathered itself from its own slow cloud of gas and dust, before the Earth had cooled, before oceans, before any night sky was here to look up into. Every small disagreement touched on tonight, the two differing rates of expansion, the surprisingly early galaxies, the stubborn shortfall of lithium, are careful notes along the edge of this one enormous, patient fact that we are always looking backward, never quite at now. Tonight, that same impossibly old light is still quietly arriving, exactly as it always has, unbothered by whether anyone happens to be awake to receive it. Carry this ancient light gently forward with you now, as this chapter settles, and we drift onward into whatever this long night still has waiting for us. Somewhere past every star you can actually pick out with your own eyes tonight, there are places where matter has gathered so completely that space itself seems to fold gently inward, and it is here, at the very edge of what can be measured and known, that our attention now turns. A black hole is not a hole in the ordinary sense at all, not some emptiness cut into the fabric of the sky, but rather a region where an extraordinary amount of mass occupies so small a space that its own gravity has grown stronger than anything else nearby, strong enough that not even light, the fastest thing that exists, can find its way back out once it drifts too close. Most of the smaller black holes scattered through our galaxy formed from the collapse of massive stars many times heavier than our own sun, their cores settling quietly inward past any resistance matter still knew how to offer. Far larger ones we will find shortly rest patiently at the centers of entire galaxies, including our own. Let your mind settle gently around this one strange, quiet idea before we walk together towards the invisible line that gives this whole chapter its name. The boundary at the edge of a black hole is called the event horizon, and despite how firm that word horizon might sound, it is not a surface at all, not something a traveler could bump against or stand upon, but rather a mathematical line marking the point past which escape, even for light, is no longer possible. The mathematics describing this particular boundary was worked out remarkably early by a physicist named Carl Schwarzschild in 1916, only months after Einstein had first published his theory of general relativity, and only shortly before Schwarzschild's own death. Cross this quiet line, according to the theory, and nothing dramatic would necessarily happen right away. No wall, no flash, no sound, only a gradual growing certainty that turning back was no longer possible. Astronomers today locate this invisible edge only indirectly, by carefully watching how light and matter behave as they draw near it, since the horizon itself, true to its name, cannot be photographed or touched directly. Rest for a moment with this quiet, careful distinction, an edge that is felt far more than it is ever truly seen. For a very long time, this particular edge remained purely theoretical, a line drawn only in equations, until a global collaboration called the Event Horizon Telescope, linking radio dishes across several continents into a single instrument effectively the size of our whole planet, managed to capture something remarkable. On the 10th of April 2019, this team released the first true image of a black hole's shadow, a glowing, uneven ring of light surrounding a dark, quiet center, belonging to the supermassive black hole at the heart of a distant galaxy called M87, roughly 55 million light-years away. That dark center held a mass estimated at some 6.5 billion times that of our own sun, and the glowing ring around it was simply superheated matter, bent and brightened by gravity as it circled the invisible edge before slipping from view. Astronomers and the wider public alike met this image with quiet astonishment, a boundary long described only in careful mathematics finally, gently made visible. Consider for a moment how strange and how patient a wait that must have been, decades of theory resolving softly into a single photograph. 3 years later, the very same collaboration turned its enormous combined gaze towards the exact center of our own Milky Way, and in May of 2022, revealed a second such image, this time of the black hole known as Sagittarius A, sitting quietly some 26,000 light-years from where you are resting right now. This one proved considerably harder to photograph than its distant cousin in M87, despite being so much nearer, since matter orbits it far more quickly, shifting and flickering within minutes rather than holding still for days, which meant the imaging team had to account for constant, restless change. Sagittarius itself carries a mass of roughly 4 million suns, remarkably modest compared with M87's own black hole, yet entirely sufficient to hold the stars of our galaxy's crowded central region gently in their long, patient orbits. Knowing that such a quiet, invisible center anchors the very galaxy holding our own sun and our own small planet is a strange kind of comfort, distant and enormous, and yet, in its own way, steady. Let that quiet center rest in your thoughts a while, unseen but certain, turning slowly at the middle of everything you can see tonight. Matter drifting too near a black hole rarely falls straight in, and instead tends to gather into a wide, flattened, spiraling structure called an accretion disk, gas and dust circling faster and faster as it spirals inward, growing hotter through friction until the innermost portions glow brightly enough to outshine entire galaxies in X-ray light. Some of this infalling material, rather than crossing the invisible edge at all, is instead redirected along the black hole's spin axis and sent back outward in narrow, tightly focused jets, streams of particles traveling at a significant fraction of the speed of light across distances of many thousands of light years, shaped and guided by powerfully twisted magnetic fields. These jets rank among the most energetic, far-reaching structures known anywhere in the universe, visible to radio telescopes long after the black hole producing them has faded from other kinds of view. It is a curious pairing, an edge that permits no return sitting calmly at the center of some of the brightest, most active objects astronomers have ever catalogued. Let this quiet contradiction settle now, gently, brightness and darkness sharing the very same origin. For decades, physicists have puzzled over what actually happens to information, the precise physical details describing everything that ever fell into a black hole, once that material crosses the horizon and the black hole itself eventually, slowly fades away. Quantum theory insists such information can never truly be destroyed, only rearranged, while Stephen Hawking's own early calculations suggested a black hole might radiate its mass away as something close to plain, featureless heat, apparently erasing that same information completely, a genuine and troubling contradiction that came to be called the information paradox. In 1997, Hawking wagered with the physicist John Preskill that this information really was lost forever, a wager he publicly, partly conceded in 2004, suggesting instead that information does eventually escape, encoded subtly within the radiation itself. Even so, precisely how that information survives and reemerges remains genuinely unsettled among physicists today, argued over in papers and conferences with real, ongoing energy rather than any tidy, agreed conclusion. Let this open question rest gently in the dark alongside you tonight, unresolved and entirely comfortable remaining so for now. That same 1974 proposal of Stephen Hawking's, the one at the very heart of the information paradox, suggested something else equally remarkable, that black holes are not perfectly, permanently black after all, but instead emit a faint, steady trickle of particles now called Hawking radiation, produced by quiet quantum effects occurring right at the edge of the horizon itself. Over unimaginably long stretches of time, this slow trickle would cause a black hole to lose mass and eventually evaporate away completely, its own edge shrinking gradually until nothing visible remained at all. For an ordinary black hole formed from a collapsed star, this predicted glow is so extraordinarily faint, and the expected evaporation so extraordinarily slow, far longer than the current age of the universe itself, that no telescope built so far has managed to detect it directly. The idea remains, then, a beautiful and widely trusted piece of theoretical physics, resting quietly on evidence that is entirely indirect, a glow imagined confidently long before it could ever actually be seen. There is something rather gentle in that, a truth patiently waiting its turn to be properly witnessed. Occasionally, a star wandering through a crowded galactic center passes close enough to a supermassive black hole that gravity begins pulling noticeably harder on the near side of the star than on its far side, gradually drawing that star out into a long, glowing stream of gas, in what astronomers gently call a tidal disruption event. Part of this stretched material eventually spirals inward, briefly brightening the surrounding accretion disk into a flare bright enough for wide-field sky surveys to catch from enormous distances, while the remaining portion is flung outward, drifting off into the wider dark beyond. Such events remain fairly rare from any single galaxy's point of view, thought to happen only occasionally, perhaps once every several tens of thousands of years within a galaxy such as our own, which makes each observed flare a genuinely valuable, closely studied glimpse into physics that otherwise unfolds far too slowly or far too quietly for us to see directly. Watching one unfold, astronomers can trace, almost step by step, exactly how matter behaves as it edges nearer that final invisible boundary. Let this rare, distant flare drift quietly through your thoughts now, one star's long, gentle farewell, observed safely from across the dark. One particular mystery tied to these largest black holes has quietly troubled astronomers for years now. The simple, stubborn question of how they managed to grow so enormous so early in the story of the universe. Surveys of the distant sky have turned up quasars, the extraordinarily bright, active centers of young galaxies, dating to less than 1 billion years after the Big Bang itself, each one powered by a black hole already carrying the mass of 1 billion suns or more. Standard models of gradual growth, matter slowly spiraling in and steadily adding mass over long stretches of cosmic time, struggle to explain how anything could reach such enormous size so quickly, leaving astronomers to consider unusual alternatives. Perhaps unusually massive seeds formed directly from collapsing clouds of primordial gas, skipping the ordinary intermediate step of becoming a star first. No single explanation has yet been agreed upon, and each newly discovered early quasar tends to make the puzzle only slightly more pressing rather than any easier to resolve. Let this particular puzzle rest quietly unanswered for tonight, one more edge, this time in time itself, that science has not yet quite managed to see past. Black holes announce themselves in one further way, not through light, but through gravitational waves, tiny ripples in space and time itself, set loose when two of them spiral together and merge into one. An instrument called LIGO detected the first such ripple in September of 2015, a signal produced by two black holes, each roughly 30 times the mass of our Sun, merging into one more than 1 billion light-years away. Later detections grew stranger still, including one announced in 2020, showing black holes of about 85 and 66 solar masses merging, sizes that theory says stars alone should not easily produce, since a range roughly between 65 and 135 solar masses was thought forbidden to ordinary stellar collapse. As this quiet chapter on black holes draws gently to its close, let every edge we have gathered tonight settle together now. Horizons that cannot be crossed, light bent into glowing rings, information debated but never lost, and space and time themselves trading places, in a sense, for anything that ventures past that final invisible line. Carry this softly forward with you now, one more boundary observed safely from a comfortable distance, as the night continues on. Deep in the southern half of Jupiter turns a single vast storm, wide enough even now to swallow the whole of Earth within its pale, banded orange. A weather system so old and so patiently watched that astronomers have followed it with real continuity since somewhere close to the 1830s. Nearly 2 centuries of steady observation, with a few uncertain records suggesting a similar marking noticed by early observers as far back as the 1660s. Though whether that was truly the same storm, no one can say for certain. Voyager's twin spacecraft, passing close by in 1979, returned the first true portraits of its slow, swirling structure, confirming what earlier telescopes had only hinted at. And yet 2 of its simplest questions remain gently unresolved even now. Careful measurement across many decades shows the storm slowly narrowing, once wide enough by older accounts to hold 3 Earths across its span, now closer to 1, the reason still not properly understood. Nor is its deep orange color explained, some compound lifted into sunlight near its clouds, the exact recipe unknown. Let this old, patient storm keep turning quietly at the edge of your thoughts now, unresolved and entirely unhurried. High above Saturn's North Pole sits a shape that seems almost too neat and geometric for something made only of moving gas, a great 6-sided current of wind, each long straight side stretching wider than the whole Earth, its corners rounding gently as the pattern turns slowly in place. Voyager's cameras caught the first hint of this hexagonal current in the early 1980s, and the Cassini spacecraft, arriving decades later, watched it persist, largely unchanged in shape, for years of close observation, its 6 corners holding steady even as seasons slowly turned across the planet far below. Unlike the drifting, shifting storms found on so many other worlds, this current keeps remarkably still relative to the planet beneath it, rotating in step with Saturn's own deep interior rather than wandering freely the way ordinary weather does. Laboratory experiments with spinning fluids have coaxed similar polygon shapes into being, hinting that winds moving at different speeds may naturally fold themselves into such neat corners, though why Saturn's atmosphere should settle on 6 sides rather than 5 or 7 is still not something anyone can fully explain. This 6-sided current can simply keep its shape now, gently overhead, quite unbothered by our not yet explaining it. Far out where sunlight itself grows thin and pale, both Jupiter and Saturn glow with a warmth that has very little to do with that distant sun at all. Jupiter radiates away noticeably more heat than it ever receives, something near 60% more by most careful estimates, a soft warmth rising from deep within the planet itself rather than borrowed from outside. Saturn, smaller and further out still, does something even stranger, giving off close to twice the energy it takes in, a gap larger, relative to its size, than almost any other planet. Part of this warmth is thought to come from gravity's own slow squeeze, each planet gradually contracting under its enormous weight and releasing a gentle trickle of heat as it does. But gravity alone does not appear to explain Saturn's full share of this warmth, leading some researchers to imagine tiny droplets of helium slowly raining downward through its hydrogen atmosphere, releasing further warmth as they sink, a graceful and still largely unconfirmed idea. There is nothing to work out tonight, only that same deep warmth, rising patiently on, entirely unseen. Uranus alone among the planets seems to roll rather than spin, tipped over so far, close to 98 degrees, that it travels round the sun almost lying on its side, poles taking turns facing the light while its equator circles them like a slow wheel. Whole seasons here last far longer than we might easily recognize, each pole settling into roughly 42 years of unbroken daylight, followed by a similarly long stretch of unbroken dark, shaped by an orbit lasting some 84 years. Quite what tipped this pale planet so dramatically onto its side remains genuinely uncertain, most researchers favoring some ancient collision early in the solar system's history, though the details are still debated. Stranger still, Voyager 2, passing by in 1986, found a magnetic field tilted some 59 degrees from the planet's own axis and noticeably offset from its center, wobbling in a way no other planet quite manages. Why Uranus alone should carry such a lopsided field is still not properly understood, though some suspect it may rise from a deep, slushy ocean of conductive fluid rather than any tidy core. Nothing here needs untangling tonight, only a whole sideways world, content to keep tumbling gently on, unresolved. Venus itself turns with almost unimaginable slowness, one rotation taking close to 243 Earth days, longer, oddly, than the planet's own year spent traveling round the sun. And yet high above that slow surface, the thick clouds of its atmosphere race around the entire planet in only about 4 or 5 days, a difference so extreme the sky seems to have forgotten the ground turning beneath it. This strange behavior, known gently among astronomers as superrotation, means the upper atmosphere circles Venus dozens of times faster than the solid planet it covers below, a gap unlike anything found on Earth, where our own winds, however strong, never outpace the ground beneath them. Early spacecraft tracking the movement of Venus's clouds first revealed this pattern decades ago, and later missions have measured it carefully again and again, confirming the effect while still not fully explaining it. Some researchers point to slow atmospheric tides raised by the sun's heat, passing momentum upward through the thick air. Others suspect deeper wave patterns still not properly mapped. Let those high clouds keep their swift, silent circling now, quite undisturbed by our still not understanding them. Far out at Saturn, its largest moon Titan holds something found nowhere else beyond Earth, real standing liquid resting openly on its surface, gathered into broad seas and smaller lakes near its north pole with names like Kraken Mare and Ligeia Mare, filled not with water but liquid methane and ethane, kept fluid only by the extraordinary cold of a world so far from the sun. When the Cassini spacecraft and its Huygens probe reached this hazy moon, descending through thick orange skies in 2005, they revealed a world with its own complete liquid cycle. Methane evaporating slowly from these cold seas, drifting upward into pale clouds, falling again as rain, and carving patient river channels down toward the lakes once more. It is, in its own quiet way, a whole weather system built from unfamiliar materials, following a rhythm remarkably similar to the water cycle we know at home, carried out at a temperature cold enough to still nearly everything else we might recognize. That same slow rain can simply keep falling now, softly, somewhere far off in the patient dark. Small, bright, and icy, Saturn's moon Enceladus keeps a genuine secret hidden beneath its frozen surface, one first properly revealed when the Cassini spacecraft, passing carefully nearby in 2005, spotted tall plumes of water vapor and fine ice particles venting steadily from long cracks near its south pole, features since nicknamed, rather gently, its tiger stripes. These graceful jets rise many kilometers above the little moon's surface, some of their finer particles escaping entirely to help feed one of Saturn's own faint outer rings, a quiet, ongoing connection between this small moon and the wide system surrounding it. Careful study of these plumes points strongly toward a genuine ocean of liquid water resting beneath Enceladus's icy shell, kept from freezing solid, most researchers believe, by the slow, patient flexing caused by Saturn's own powerful gravity as the little moon travels its orbit. What exactly warms this hidden sea so consistently, and what chemistry might be unfolding within its dark water, remains gently uncertain, one of the more patient mysteries among these icy outer worlds. Let this small, patient mystery rest here a while longer, gently, with nothing further asked of you tonight. Mars, for all its cold and thin, quiet air, still manages storms of a remarkable scale. Ordinary regional dust storms rising with some regularity from its dry, red surface, and on rarer occasions swelling until fine dust spreads entirely around the planet, wrapping the whole world in a pale, hazy veil for weeks or even months at a stretch. One such storm, gathering through the middle of 2018, grew so complete that it finally darkened the sky above NASA's Small Opportunity rover until its solar panels could gather no further light, bringing, after many faithful years of work, a gentle and final silence to its mission. Quite why some regional storms fade quietly away within days, while a rare few keep growing until they encircle the entire planet is not yet properly understood, even though Martian dust storms have been watched carefully across many years by orbiting spacecraft. These planet-wide storms tend to gather during the warmer months of the southern hemisphere, when Mars sits closest to the Sun, though not every such season produces one. Let that fine, drifting dust settle now, unseen, across a world already resting quietly behind us. Deep within the thick, swirling clouds of Jupiter and Saturn, storms produce something quietly familiar from our own night skies. Flashes of real lightning, bright and brief, born from towering clouds of water far below the calmer, paler layers we see from outside. Voyager's cameras caught the first hints of Jupiter's lightning decades ago, and later spacecraft, including Juno in more recent years, found flashes occurring not only deep within these water clouds, but rather unexpectedly, much higher up too, in colder regions mixed with ammonia, a discovery that quietly complicated what scientists had long assumed. Saturn II carries its own lightning, first detected through bursts of radiostatic picked up by the Cassini spacecraft, and finally seen directly as genuine flashes of visible light during an enormous storm that circled the planet through 2011, the first time such lightning had ever actually been photographed there. Exactly how these distant storms generate and distribute their lightning through such strange, layered atmospheres is still being worked out, each new spacecraft adding a little more detail without yet completing the picture. Such a small, hidden flash needs no more from you tonight than a little quiet, unhurried notice. Out at the edge of our tour of storms lies Triton, Neptune's largest moon, a small, frozen world where Voyager 2, passing by in 1989, found dark streaks scattered across a bright southern polar cap of frozen nitrogen, traces of quiet geysers, thin plumes of nitrogen gas and dust rising several kilometers before drifting downwind and settling back onto the surface. These plumes seem driven by sunlight itself, warming pockets of nitrogen ice trapped beneath a clearer surface layer until the gas breaks free, a gentle trigger for a genuinely cold and distant kind of weather. Because Neptune's own year lasts some 165 Earth years, Triton's seasons stretch far beyond any single human lifetime, its polar caps shifting slowly across decades upon patient decades. As this long, slow chapter of restless winds and quiet, unanswered storms settles now, let its whole shape rest in your mind. A red spot slowly narrowing, a six-sided current turning in place, warmth rising within two great planets, a sideways world with its wandering magnetic field, and one small, frozen moon still faintly venting into the dark. Carry it all softly forward now, however this long, unhurried night chooses to continue. Somewhere in the deeper hours of this long night, we step toward the places where physics begins to strain at the edges of what it can confidently explain. And there is no better place to begin than the neutron star, the collapsed heart of a star far larger than our own sun, crushed by its final explosion into a sphere perhaps 20 kilometers across, no wider than a modest city, yet holding more mass than the sun itself. The density defies easy comparison, though physicists have long reached for the same domestic image, that a single teaspoon of neutron star material, weighed on an ordinary scale, would come to something in the order of 1 billion tons, heavier than a mountain, heavier than anything so small has any right to be. And yet for all this confident arithmetic, what actually fills a neutron star's interior remains genuinely unresolved. Whether a strange superfluid of neutrons, layers of matter arranged like pasta, or something stranger still pressed at its core. A question physicists simply call the equation of state, unanswered after decades of careful work. Let that number rest quietly in your mind, too strange to picture and too certain to doubt, before we drift gently onward. In the summer of 1967, a young postgraduate student named Jocelyn Bell Burnell sat night after night at Cambridge, combing patiently through meters of chart paper from a radio telescope she had helped build herself, a sprawling field of wires and posts meant to study the flickering radio glow of distant quasars. Buried in that paper trail, she noticed something the instrument was never meant to find, a signal pulsing with an almost impossible regularity, arriving again and again, every little over a second, far too precise to match anything then known to occur naturally among the stars. For a brief, half-serious stretch of time, she and her supervisor privately nicknamed the signal Little Green Men, entertaining the strange possibility of an artificial beacon before the far stranger truth revealed itself. What she had actually found was a pulsar, a rapidly spinning neutron star sweeping a narrow beam of radio light around itself like a lighthouse turning in the dark, visible to us only in the brief instant that beam sweeps across the Earth. Let the discovery settle now, gently, the way any honest and quiet surprise eventually does, before we follow it further into the dark. Once astronomers understood what Jocelyn Bell Burnell had found, they turned to something almost as remarkable, the sheer precision with which a pulsar keeps its rhythm, each spinning neutron star turning on its axis with a regularity that rivals, and in certain cases matches, the finest atomic clocks built in laboratories on Earth. Ordinary pulsars turn once every second or so, while millisecond pulsars spin hundreds of times in that same single second, each sweep of their beam arriving with a timing so dependable that astronomers have learned to set their calculations by it, much as earlier generations set theirs by the steady swing of a pendulum. This reliability comes from simple physics rather than mystery, a small, dense body left largely undisturbed in the emptiness of space, with almost nothing around to slow it or nudge it off its rhythm. Vast networks of these pulsars, scattered across the galaxy, are now watched together as a kind of natural cosmic clock, astronomers hoping their combined ticking might one day reveal the faint ripple of a gravitational wave. Hold that steadiness quietly for a moment, the way you might hold the tick of a clock you trust completely, before we let it go. Among the strange relatives of the ordinary neutron star, the magnetar stands apart for one reason. a magnetic field so powerful that ordinary language struggles to hold it, commonly described as many hundreds of trillions of times stronger than the modest field that quietly guides a compass needle here on Earth. Physicists illustrating this scale have offered a gentler comparison, that a magnetor's field, brought merely to within the distance separating the Earth from the Moon, could in principle wipe the data from a credit card clean, a small and strangely relatable measure of something otherwise almost impossible to imagine. Such fields are thought to arise from the same collapsing process that forms any neutron star, only compressed further still, twisting the star's own magnetic structure into something tighter and far more intense than its quieter cousins ever achieve. From time to time, a magnetor's rigid crust appears to crack under the strain of its own field, releasing a sudden, enormous burst of gamma rays in what astronomers call a starquake, detectable from clear across the galaxy. There is no need to hold on to any of this too tightly tonight, only to let its strangeness pass softly through your tired mind. For all their famous steadiness, pulsars occasionally do something that quietly unsettles the reliability that makes them useful. A sudden, tiny jump in their spin, speeding up in an instant rather than slowing gradually the way friction and radiation would otherwise predict, an event astronomers have come, simply and fondly, to call a glitch. These glitches happen without warning, often only microscopic in size, a fractional change in rotation that only patient timing could ever notice. And yet they happen consistently enough across enough pulsars that they clearly belong to something real rather than simple error. The leading explanation imagines the neutron star as two loosely connected parts, a rigid outer crust spinning at one steady rate and a strange superfluid interior spinning slightly faster, occasionally slipping and transferring its motion outward to the crust, rather like a coat lining briefly catching before settling again. Yet the finer details, exactly when a glitch will occur, exactly how large it will be, remain genuinely difficult to predict, a small acknowledged gap in our understanding of matter behaving under conditions no laboratory on Earth could recreate. Let this small uncertainty rest easily beside you now, unresolved and entirely fine to leave that way. Far beneath the ordinary surface of the Earth, hidden inside old mines and carved deep beneath solid rock or ancient Antarctic ice, sit some of the strangest laboratories ever built, vast tanks holding tens of thousands of tons of extraordinarily pure water, or a full cubic kilometer of clear polar ice threaded through with light sensors, all built for the sole quiet purpose of catching a single, almost weightless particle called the neutrino. Neutrinos pass through ordinary matter so easily that trillions drift harmlessly through your own body every second, unnoticed, gone before you could ever hope to feel them, which is precisely why catching even a rare few requires such enormous tanks. Buried deep underground, shielded from the static of ordinary cosmic rays raining down from above, these detectors wait quietly for the vanishingly rare occasion when a neutrino strikes a nucleus or an electron, producing a brief, faint cone of blue light that sensors lining the tank's dark walls are built to notice instantly. Down there in that permanent underground night, nothing moves and nothing sounds, only that occasional, soundless flicker of blue, patiently awaited. Nothing more needs to be understood about this tonight, only felt quietly before we drift on. For nearly 3 decades, one puzzle involving these same shy particles troubled physicists studying our own sun, beginning in the late 1960s when Raymond Davis and his colleagues, working with a tank of cleaning fluid buried inside the Homestake gold mine in South Dakota, counted only about 1/3 of the solar neutrinos that careful calculations said the sun ought to be producing every moment. For years, this shortfall, known as the solar neutrino problem, left physicists uncertain whether the fault lay with their understanding of the sun, of the neutrino, or with the delicate instruments straining to count something so faint. The eventual answer, confirmed around the turn of the millennium by a heavy water detector in Sudbury, Ontario, was almost gently poetic. The missing neutrinos were never missing at all, only traveling in disguise, changing from one flavor into another during their long journey from the sun's core, slipping past detectors built to notice only one kind. This discovery, called neutrino oscillation, quietly rewrote what physicists thought they knew, and it eventually earned its investigators a shared Nobel Prize. There is a certain piece in a puzzle this old finally being answered, and that piece is enough to rest on now. In a quiet laboratory hall west of Chicago, physicists have spent years watching a single, delicate wobble, the way a muon, a heavier cousin of the electron, behaves as it circles endlessly inside a great superconducting ring magnet, 50 feet across, once carried up the Mississippi River by barge, then driven the last miles by truck to its current home. As each muon circles the ring, it spins gently on its own axis, wobbling very slightly in the magnetic field, an effect physicists can predict to an almost absurd number of decimal places. And it is in exactly those final, faint places that something curious now appears to linger. The measured wobble, gathered across years of careful runs, sits slightly, persistently off from what the accepted theory predicts. A gap small enough that it might resolve itself through refined calculation, and yet large enough that some physicists suspect it may be quietly hinting at particles or forces no one has detected before. Neither side of that quiet disagreement has yet convinced the other, and the question remains genuinely, respectably open. Let that small, persistent wobble settle now in the dark behind your eyes, unresolved and entirely undemanding, before we drift on. Many of the experiments patient enough to chase these faint mysteries share a working environment that feels, in its own way, remarkably close to sleep itself. Laboratories cooled by careful stages down toward temperatures colder than the empty space between stars. Chambers pumped free of nearly every stray molecule of air, until what remains counts as one of the emptiest volumes ever created by human hands. Physicists chasing the faintest possible signals, a single trapped atom, a whisper of gravitational strain, a rare flash of captured light, have learned that warmth, vibration, and stray air are quietly hostile to delicate measurement. So the rooms housing this work are often built to be still in ways few other places on Earth ever are, floated on isolated foundations, wrapped in layers of shielding. Kept deliberately dim, since even ordinary light can disturb the most sensitive instruments. Researchers working near such chambers speak of a particular hush that settles over these spaces, a stillness kept not from any preference for quiet, but because the smallest secrets refuse to reveal themselves in anything less than near total silence and near total dark. Consider that hush for a moment now, and let it settle gently over you as well. As this chapter of straining physics draws toward its close, consider one final, tender discovery, that time itself, which feels so steady and uniform to each of us, actually passes at slightly different rates depending on how deep within a gravitational field a clock happens to sit. A prediction confirmed as early as 1959, when Robert Pound and Glenn Rybka measured a tiny shift in falling light inside a tower at Harvard. Modern atomic clocks have since grown sensitive enough to notice this same effect across absurdly small distances. Experiments showing measurable differences between a clock resting on the floor and another resting on a shelf barely a foot above it. The higher clock, ever so slightly, ticking faster. Satellites orbiting overhead feel this same effect constantly, their onboard clocks running fractionally faster than ours by sitting farther from the Earth's pull. A difference so real that positioning systems must correct for it daily to stay accurate. Tonight, wherever you happen to be resting, time is passing over you at its own particular, gravity-shaped pace, gently, exactly as it always has. Rest here now in that soft uncertainty, the kind that never needs solving before sleep is finally allowed to come. Among the many stars watched by the Kepler Space Telescope, one stood out for behaving in a way no ordinary star should, an otherwise unremarkable point of light in the constellation Cygnus, later nicknamed Tabby's star after Tabitha Boyajian, the astronomer who led the team studying it. The star dimmed in brief, irregular episodes following no repeating rhythm, unlike the clean, evenly spaced dips a transiting planet produces, and on one occasion it faded by as much as 22%, far too deep and uneven for any planet to explain. Citizen scientists combing through the telescope's data noticed the pattern first, and once astronomers examined it, one idea proposed at the time, among several others, was that a vast artificial structure might be orbiting the star, worth testing simply because it could be tested. Careful follow-up observations, watching the star fade in different colors of light at once, showed the dimming ran deeper in blue light than in red, exactly what fine dust would produce and a solid object would not, quietly settling the question towards dust rather than anything built. The mystery once so loudly discussed now rests gently on a far simpler answer. Far across the constellation Serpens, roughly 600 million light-years away, sits a galaxy so tidy in shape that photographs of it are sometimes mistaken for diagrams rather than real images. A nearly perfect ring of young, blue-white stars circling a smaller, rounder core of older, yellowish stars, with a wide, dark gap of empty space separating the two. First described by the astronomer Arthur Hogue in 1950, this object, which now carries his name, spans roughly the width of our own Milky Way, and unlike most galaxies, which sprawl into loose spirals or uneven blobs, its ring holds together with a symmetry that looks almost deliberately drawn. Astronomers generally suspect it formed through a slow accretion of gas, or perhaps a close encounter with another galaxy long since scattered or absorbed, drawing outer material into this smooth circular band of star formation, though exactly how such a clean ring emerged, without the usual visible wreckage such encounters leave behind, remains only partly settled. Curiously, if you look closely through the gap on one side, a second, smaller ring-shaped galaxy, entirely unrelated and much farther away, sits almost perfectly framed within that empty space. Let that quiet coincidence of shape rest gently in the mind. Spread across the entire sky is the faint afterglow of the universe's earliest light, the cosmic microwave background, remarkably even in temperature from one direction to another, which is precisely what makes one patch of sky, towards the faint southern constellation Eridanus, so difficult to fully explain. First noticed in data from the WMAP satellite in the early 2000s and later confirmed by the Planck mission, this cold spot covers some 5 to 10 degrees of sky, far larger than ordinary statistical variation should allow, and measures cooler than its surroundings by a small but genuinely puzzling margin. One leading explanation points to a supervoid lying roughly along the same line of sight, an unusually empty stretch of space nearly 2 billion light-years across, whose gentle draining effect on photons passing through it could account for at least part of the chill. Deeper surveys, however, have questioned whether that void is quite large or quite empty enough to explain the entire effect alone, leaving the matter open rather than closed. No dramatic answer has been required to keep studying it, only patience and the slow accumulation of better maps. Let this quiet, cool patch of ancient light settle now, unresolved but calmly held. Our own Milky Way, along with thousands of neighboring galaxies making up the local group, is drifting steadily through space at hundreds of kilometers each second towards a single, shared destination. A concentration of mass astronomers named, quite simply, the Great Attractor. Its pull was first noticed in the 1980s, when researchers studying the motion of distant elliptical galaxies found they were not moving quite as the overall expansion of the universe would predict, but were instead being tugged sideways, towards a region roughly 200 million light-years away in the direction of Centaurus and Norma. For a long while this region resisted easy study for a rather ordinary reason, since it lies almost directly behind the crowded, dusty disk of our own galaxy, a stretch of sky astronomers call the zone of avoidance, hidden behind our own stars and gas rather than anything more unusual. Radio and X-ray telescopes, able to see through that dust where ordinary starlight cannot, eventually revealed a genuine cluster of galaxies anchoring the pull, now understood as part of the vast Laniakea supercluster, our own home address on the largest scale astronomer's map. It is, in the end, simply gravity, exercised patiently across an enormous hidden crowd. In 1981, a team of astronomers led by Robert Kirshner, surveying galaxy distances in a broad patch of sky towards the constellation Boötes, noticed something that at first looked like a gap in their data, a huge stretch of space containing hardly any galaxies at all, so empty the team reportedly joked it could hold dozens of Milky Ways stacked one beside another without touching. Later, more careful surveys settled its true scale at somewhere around 330 million light-years across, with only a small handful of galaxies confirmed sitting genuinely inside it rather than appearing there by chance alignment. Such enormous voids are not, on their own, a violation of modern cosmology, since the standard picture of structure formation predicts matter should drain gradually out of underdense regions over billions of years, pulled by gravity into the surrounding filaments and walls of galaxies that give the universe its familiar, web-like shape. What makes the Boötes void worth pausing on is simply its scale, sitting near the upper edge of what such natural emptiness is expected to produce, a reminder of how much of the universe, even now, remains quiet and unoccupied. Let this vast, patient emptiness settle now, exactly as it is. In 2013, a team of astronomers working from the positions of distant gamma-ray bursts proposed an almost unimaginably large structure stretching across Hercules and Corona Borealis, estimated to span something on the order of 10 billion light-years, which, if confirmed as first described, would rank among the largest structures ever proposed. This claim sits uneasily beside one of the founding assumptions of modern cosmology, the idea that matter, averaged across large enough distances, should appear roughly even in every direction, with theoretical work generally suggesting genuine structures ought not exceed somewhere around 1 to 1.5 billion light-years before that evenness takes hold. A structure many times that size raises an honest methodological question rather than a dramatic one. Since gamma-ray bursts are rare, their distances carry real uncertainty, and grouping them across such vast volumes can sometimes create the appearance of connected structure where none physically exists, a possibility several researchers have argued directly. Whether this proposed wall is a genuine, bound structure or a statistical shape drawn from too few points remains an unsettled question. It rests, for now, exactly where careful disagreement leaves it. Dark matter, whatever it ultimately turns out to be, accompanies nearly every galaxy ever studied, typically outweighing the visible stars within it many times over, which is what made one particular galaxy, reported in 2018 by a team led by Pieter van Dokkum, such a surprise, a diffuse, faint galaxy roughly 60 million light-years away that appeared to contain barely any dark matter at all. Astronomers reached this by measuring the motion of small clusters of stars orbiting within the galaxy. Finding their speeds implied a total mass close to what the visible stars alone could account for, leaving little room for anything unseen alongside them. A second, similar galaxy nearby soon showed much the same puzzling pattern, and although some researchers initially questioned whether both galaxies might simply be closer than assumed, which would ease the discrepancy, later distance measurements tended to support the original, more surprising conclusion. One leading explanation suggests these faint galaxies may be leftover debris from an ancient, high-speed collision between other, gas-rich galaxies, flung outward in a way that separated ordinary matter from whatever dark matter had once traveled alongside it. Such galaxies remain rare, small exceptions testing a rule that otherwise holds almost everywhere else. Comets passing near the sun typically grow not one tail but two, a broad, curving tail of dust, pushed outward by the faint pressure of sunlight and trailing behind the comet's own path, and a second, straighter tail of ionized gas, glowing pale blue, pushed directly away from the sun by the solar wind. Occasionally, though, photographs of a bright comet appear to show a third tail, a thin spike seeming to point the wrong way, towards the sun rather than away from it, an anti-tail that startled observers when it first appeared prominently on comet Arundroland in 1957, spread across news photographs of the time. The explanation, once worked out, turned out to involve no strange new physics, only geometry, since larger, heavier dust grains left behind along the comet's orbital path spread slowly into a broad, flat sheet. And when Earth happens to cross close to that same orbital plane, this sheet can appear, purely from our viewing angle, to project sunward even though every grain within it continues moving quietly along its ordinary trailing path. Comet Hale-Bopp displayed a softer version of the same illusion in 1997. It is simply perspective, briefly dressed as something stranger. Deep within the Eagle Nebula, several thousand light-years away, towering columns of cold hydrogen gas and fine dust rise several light-years tall, sculpted into their familiar finger-like shapes by fierce ultraviolet light and stellar winds pouring outward from a cluster of massive young stars nearby. Radiation that slowly erodes the thinner surrounding gas, while denser knots resist far longer, left standing like patient towers above the gas being carried away. Photographed by the Hubble Space Telescope in 1995, in an image that became one of the most recognizable pictures in modern astronomy, and again by the James Webb Space Telescope decades later in far greater detail, these pillars turned out to hold small, dense knots at their tips where new stars are actively forming, tiny stellar nurseries tucked inside the very structures being slowly worn away around them. One infrared study suggested a nearby supernova may have already destroyed the pillars themselves thousands of years ago in a fast-moving shockwave, though because of the distance involved, any light showing that destruction has simply not finished its journey towards you yet. What we still see, then, may be a faithful echo of towers already gone. The bright nearby star Fomalhaut, some 25 light-years away, is circled by a wide, well-defined ring of dust and debris, and in 2008 astronomers announced they had photographed something else within that ring, a faint point of light they called Fomalhaut b, celebrated as one of the first planets ever directly imaged outside our solar system. Over the following years, though, this point of light behaved less and less like an ordinary planet, showing none of the warm infrared glow a true planet of its size should carry, and drifting on a path that looked less like an orbit and more like something slowly expanding and fading. A careful reanalysis published in 2020 concluded that Fomalhaut b was most likely never a planet at all, but rather an expanding cloud of fine debris, probably thrown outward by a collision between two large icy bodies within the ring, a cloud that has since thinned and faded until it can no longer be seen. The ring itself remains, patiently sculpted into its narrow shape, most likely shepherded gravitationally by some planet still hidden from direct view, its presence inferred only from the ring's own tidy edges. Even a careful photograph can quietly change its story. By the time the deepest hour of the night has quietly come and gone, a different mood begins to settle over any place on Earth where a telescope still stands open to the sky, a mood less of discovery than of gentle, unhurried completion. The stars that have wheeled overhead for so many hours begin, ever so slowly, to lose their sharpest edge against a sky that is not yet light but no longer perfectly dark either, and anyone still awake tends to feel this shift before being able to properly name it. On mountaintops in Chile, in Hawaii, and on the Canary Islands, domes that have stood open since dusk begin their own unhurried preparations for closing, cameras finishing their last exposures while operators glance, again and again, towards the eastern horizon. This final stretch of the night belongs to that particular corridor of time between the deepest dark and the first true light, when astronomy does not so much stop as change its shape, folding its attention inward, towards data already gathered, towards calibration, towards rest. Let this slow turning settle over you gently now, as we walk through it together, one small and unhurried fact at a time. As this last corridor of darkness begins, astronomers still awake on any given mountain move through a closing routine so familiar it has become almost a ritual, checking the night's final images and preparing the great dome to be sealed against the coming day. Domes close not at sunrise itself, but earlier, once the sky begins to brighten enough to scatter unwanted light into even the most carefully shielded instrument, since one faint galaxy can be washed out entirely by a sky that still looks, to the naked eye, comfortably dark. Humidity and wind sensors also help decide the moment, since a mirror left open to gathering dew or a sudden gust of dust-laden air can undo careful work in moments. Somewhere on such a mountain, right about now, a heavy shutter begins its slow mechanical rotation, sealing tons of curved glass safely away from the pale light gathering beyond the dome's slit. Whatever the telescope has gathered through the night now belongs to the hours ahead, to careful hands and quiet processing, rather than to the sky itself. There is nothing dramatic in any of this, only one more familiar door easing gently shut before the coming day. The word twilight, so often used loosely to describe any dim and softening light, actually carries a far more precise meaning for astronomers, who divide this long transition between night and day into three distinct, carefully measured stages. Civil twilight begins first, while the sun still rests less than 6 degrees below the horizon, a stage bright enough that most ordinary outdoor activity remains comfortable without artificial light. Nautical twilight follows, spanning the point where the sun sits between 6 and 12 degrees below the horizon, named for the era when sailors could still make out the horizon line clearly enough to take star sightings for navigation. Astronomical twilight comes last and faintest of the three, lasting until the sun has sunk fully 18 degrees beneath the horizon, and only once that threshold is crossed does the sky grow dark enough for the faintest galaxies and nebulae to reveal themselves properly to sensitive instruments. Before dawn, this whole sequence simply runs in reverse, astronomical twilight arriving first as the sky's true blackness begins ever so slightly to soften. It is this quiet, precise boundary, 18 careful degrees, That tells a waiting telescope exactly when its own working night has gently ended. In the hour or two before true sunrise, on a clear morning far from any city's glow, a patient observer facing east might notice a soft, faint, slanting pyramid of light rising from the horizon and leaning up along the path the sun itself will soon follow. This gentle glow is called the zodiacal light, sunlight scattering off countless small particles of dust drifting through the inner solar system, shed long ago by passing comets or stirred loose from collisions among asteroids, all settled roughly into the same flat plane in which the planets themselves travel. Because that dust plane traces the same path across our sky as the sun, moon, and planets, the zodiacal light leans along that familiar band of constellations known as the zodiac, faint enough that moonlight or the smallest hint of artificial light can hide it completely. Some early risers, glimpsing this soft cone of light and mistaking it for the first hint of coming day, once called it the false dawn, a gentle misunderstanding that still feels rather touching. It is a small, gentle trick of scattered light, offered quietly, before the true dawn follows properly along behind it. Long before dawn's true light arrives, one point of brilliance often hangs low and unmistakably bright in the eastern sky, outshining every star around it, a planet the Romans called Lucifer, the light bringer, when it appeared in the morning like this, and Vesper when that same brilliant point greeted the evening sky after sunset. This is Venus, and its habit of appearing only near sunrise or sunset, never at any other hour, comes from its orbit lying closer to the sun than our own, so that from Earth it can never wander far from the sun's glow. For a long while, many early sky watchers assumed Lucifer and Vesper were two separate objects, one belonging to morning and one to evening, an easy mistake given that the two were never once seen sharing the sky together. Babylonian astronomers, keeping careful records across many generations, seem to have worked out the truth long before most others, and later Greek tradition often credits the philosopher Pythagoras with announcing what patient observation had already shown, that morning star and evening star were simply one and the same bright world. Let this old, gently corrected confusion settle now, softly, the way any long misunderstanding eventually does. As the eastern sky continues its slow brightening, the stars do not vanish all at once but fade from view in a fairly predictable order, faintest first, as though the sky were gently erasing its own dimmest pencil marks before moving on to bolder ones. Stars that required a properly dark sky to be seen at all disappear within the earliest, gentlest stages of dawn twilight, while the handful of truly bright stars, along with any visible planets, continue holding their ground against a sky steadily filling with pale, competing light. Sirius, the brightest true star in the entire night sky, is very often among the last of them to surrender, a single steady point refusing to fade until the sky around it has grown almost fully light. Venus, brighter still than any star, can sometimes be traced by a patient and practiced eye well after actual sunrise, a small, pale, determined presence visible against blue daylight to someone who already knows exactly where to look. Tonight, whichever bright point happens to hold on longest over your own horizon, know that it is simply following this same old, orderly pattern, brightness itself deciding, quietly, who gets to stay a little longer. Contrary to what the word midnight might seem to promise, the coldest moment of the day rarely arrives at that hour, but instead settles in later, closer to sunrise, since the ground continues radiating its stored warmth into the clear night sky for as long as darkness lasts, with nothing yet arriving from the sun to replace it. On the clearest, calmest nights, the same still, cloudless conditions that give a telescope its steadiest view of the stars Also let this cooling continue most efficiently. So dawn on a good observing night is very often a properly cold one. As the air just above the ground cools past a threshold called the dew point, moisture already present in it can no longer stay suspended, and settles instead onto grass, metal railings, and any other surface that has cooled quickly enough, gathering there as the small beads of dew that catch the very first color of morning light. Telescope domes and lenses face this same gentle threat, fitted often with small heaters meant to keep dew from settling where it would blur or fog a carefully kept mirror. Let this small, cold truth settle now, quietly, the way dew itself settles, without any hurry at all. Once the dome has closed and the astronomers have gone to whatever rest they can find, the telescope's own working day, in a real sense, is only just beginning, since the images gathered through the night still need turning from raw, imperfect data into something a human mind can properly use. Calibration frames are taken and applied, dark frames capturing the instrument's own faint internal noise, flat fields correcting for tiny unevenness across the camera's sensor, each a small correction layered quietly beneath the starlight captured hours earlier. Daylight hours also belong to maintenance, engineers moving through empty domes to clean optics, calibrate instruments, replace worn components, and occasionally recoat a mirror's reflective surface after years of faithful service. Elsewhere in offices and universities scattered across different time zones, other astronomers are only now waking to download the previous night's results, sorting through them for anything unexpected, anything moving, anything simply not there the night before. In this quiet way, the telescope's night never really ends so much as it changes hands, passed onward from starlight to circuitry to careful human attention. It is, in its own quiet way, simply one more shift change in a night that never fully sleeps. Even as older telescopes close their domes for the day, newer instruments are being built to change this whole patient rhythm. Among them, a new generation of wide-field survey telescopes designed to photograph enormous stretches of sky in a single exposure and return, again and again, to the same patch of stars every few nights rather than every few years. One such observatory, built high in the mountains of northern Chile, carries a camera large enough to capture the entire visible sky roughly every 3 or 4 nights, comparing each image against those before it in search of anything that has moved, brightened, dimmed, or simply appeared where nothing sat before. Across its first years of operation, such a survey is expected to uncover more new asteroids, exploding stars, and briefly flaring objects than all earlier telescopes combined ever managed to find, quietly rewriting our sense of how much motion fills a sky that so often looks, to ordinary eyes, perfectly still. Tonight, somewhere on that distant mountain, a camera may already be turning from one patch of sky to the next. Let this quiet, patient flood of new discovery settle over you now, gently, before we come to this long night's final thought. After 99 such small mysteries, gathered slowly across this whole long night together, it would be reasonable enough to hope that 100th fact might finally close the list, tying every loose thread into something neat and settled and complete. But that is not, in truth, how any of this works, since every question this vast sky has quietly answered across the centuries has tended to open 2 or 3 new ones in its place, each discovery revealing the soft, faint outline of some larger question waiting just beyond it. Every one of those future survey telescopes we have imagined, scanning the sky again and again for anything new, will not empty this list so much as lengthen it, finding stranger and more distant things to quietly wonder about. And this, rather than being any kind of defeat, feels instead like something close to a gift, A sky so large and patient that it will always hold a little more than we currently understand, always leave a little more waiting gently for tomorrow's careful attention. This is simply what a good sky does, quietly leaving room for one more question, and there is nothing left now but to rest inside that small, unfinished space. That is 100, and the sky has gone quiet. Every single one of them is still open. Somewhere tonight a telescope is still pointed at one of these, and someone is still waiting for an answer, patiently, the way people have waited for a very long time. None of it needed solving tonight. It was only ever there to be looked at. The dome is closing now. There is a thin gray line along one edge of the sky, and the rest of it can wait until tomorrow, the way it always does. If this kept you company, there is a new one of these every week, and it will be here whenever you need it. Sleep well. The sky will still be there in the morning, and so will everything we have not worked out about it yet. QC, chapters equals 10 facts equals 100 words equals 20,381.